خير
معلم.
البرية كاع ما
تفهمني.
احسن حاجه هي البريه كاع. لا
تكون في المطور.
لا
بلدي يعجبني انا عشت بلدي.
البريه لا كون بلع على البريه. لا والو انا ما فهمتنيش. البريه ابار بلعه وحدها.
وعلاه بغيت تكون البريه محلوله؟
لا ما راكش فاهم. كابور خلصه كاين واحد البريه بوحدها. لا شوف فيها السميه كيف
خليل قول له على القيمه ديال المحلول كيما القيمه ديال المبلع.
This meeting is being recorded.
سالي كانوا كتحك عرفت فين
انا ماشي.
انا نعم
انا ما قلتش
ماشي عرفت قبيله اللي راني عارف
نقول له الناس على ظهرك. وكنت عاز عليك تسمع باش كنت تفكر.
سير تشوف هذا الحموان هذا
شنو نقول لك هذا خالد الدبيت لقى مع محمد شنو نقول لك يجيب له اساس يقول له اليوم يقول واش النهار عندي هذا مليون يقول له شو دير معايا ديري انا ديال الفوبيا يقول له 60000 مليون ريال لا ولكن 60000 يبان لي راهم فاهمين الله يسهل عليهم زعما.
اللون هذا بحال هذا اللون كتزيد
هذا شيء
الا قبضتها وديتها للدار هذا حتى لا
السماوي الطلاسم
شوف كديرها هي كيلقى حفر كيوجد
البريات
تيوا صافي راه عندك انت بحال هذا عندك المعلومات زوم عندك 14
نتصل نقص.
No, YouTube.
from YouTube.
I think Zoom is okay. YouTube is your speaker.
لا في هذه في افريقيا بلوكي هنا في الشتي الخريطه ديال المغرب ولا
Ladies and gentlemen, we can start the
شوف خلي هذيك ستوندار خليها هذيك اللي غادي
given by Professor Mustafa Busumina. Professor Busumina has held the prominent academic positions, including serving as
هذه من نص سنه قلنا نخليها ستوندار.
in Canada Research Chair in Polymer Physics and Nanomaterials at Laval University in Quebec, Canada. He is also been the Director General of the Institute of Nanomaterials and Nanotechnology in Morocco from 2008 to 2011. Beyond his role at UMNF, he was the Chancellor of the Hassan II Academy of Science and Technology in Morocco and the President of the Network of African Academics of Science. Also, Professor Busumina is currently President of African Science and Research Innovation Council, which is the prominent body for financing the research in Africa, and he's also president of Oromed University in Fes. And Professor Busumina has made significant contributions to the field of polymer processing and nanomaterials, notably he developed an equation that allows the extraction of shell rate and stress from matrices of any geometry, which has been implemented in the commercial mixers worldwide. This is quite important that we know and important. The science is not implemented that question why we are doing it. Professor Busumina work has been recognized with several awards, including the Louis Pasteur Award in 1993, the Morand Langlois Award from the Polymer Processing Society in 2000, and many others. So, Professor Busumina, I would like to invite you for a speech, and please.
Can you switch the video? The presentation.
Thank you, Mr. Speaker. First of all, I would like to express my high appreciation to the organizers for this kind invitation to give a talk on energy, water desalination, and green hydrogen nexus. I will basically present the state-of-the-art kind of currently used technologies, pointing out the challenges, the bottlenecks, and the problems we are facing in terms of science and technology nowadays. But instead of making an off-the-ground kind of presentation, it seemed to me that it is more relevant and more pertinent to connect my presentation to Morocco's needs. To Morocco's needs in terms of water, in terms of energy, and those of you who don't have much information about Morocco, my country, Morocco, is situated in North Africa, 14 kilometers away from Spain, from Europe. The population of Morocco is 37 million. We have a total surface area that exceeds 700,000 kilometers square. We have two coastlines with a 3,005 kilometer, 500 kilometers on the Mediterranean shore, and 3,000 kilometers on the Atlantic. My country is situated in a very dry zone. So water scarcity, it's very dramatic in this country. It presents a big threat to the development of my country. At the same time, Morocco has no gas, no oil, no many natural resources. The only thing we have just human resources. And we are importing more than 88% of our energy needs from outside. So before going to science and technology, please allow me to present briefly why this energy, water desalination, green hydrogen nexus is very important to Morocco. And at the same time, it might be also, the things that I will present might be also of interest to other countries. But to do that, let me present to you briefly the Morocco's. Comment ça se fait? Je n'arrive pas à faire passer. يعني بغيت نجي لتحت.
لافيشاج ما كاينش.
ها؟
بروبليم ديال لافيشاج.
شنو؟
بروبليم دافيشاج.
بروبليم دافيشاج هذا هو il faut le résoudre بروبليم دافيشاج. Is there someone who can help here for the computer? Est-ce qu'il y a quelqu'un qui peut aider?
Yes, I tried, but I'm not sure about it.
لا خلي السيد يلا سيدي. حيدوا كوبي هذاك شي ياخذ لك ما هذاك باش ديروه في.
لا أنا أنس
transition. Transition.
We are sorry for the technical
Doesn't
difficulties. Yeah, it's. Sometimes we cannot influence on these things. Yeah. Okay.
Is it okay? But now,
It's too big screen.
big, we cannot see.
Yeah, it's a resolution problem.
Okay?
Okay.
Okay. So my presentation will go as follows. In the first part, just briefly, I will present the pillars, the fundamental pillars of the Morocco's economy and its strategy in terms of energy, water desalination, and production of green hydrogen. Then I will move to scientific part by presenting some blocks of this nexus, basically fuel cells, electrolyzers, and batteries. Then I will explain the problems we have with osmosis for water desalination. Then I will present some new technologies that allow extracting or generating energy from sea waves. And if I have time, I will present some ongoing projects that combine artificial intelligence and agriculture for management of water and fertilizers. And I will end my presentation by some concluding remarks. So in 3 slides, I will explain why this is very important to my country. These are the pillars of Morocco's economy. The first pillar of Morocco's economy is automotive and aeronautics industry that accounts for more than 20% of our national GDP and more than 25% of Morocco's exportation. And more than 58% of the entire Africa's exportation in the field of automotives and aeronautics comes from Morocco. We don't have gas, we don't have gasoline, but yet Morocco is the first car manufacturer in Africa. We produce annually 700,000 cars. We will increase by 2030 more than 1 million cars per year. We have the first aeronautic facilities in the continent. There is no one airplane presently that is flying on the sky that has not at least one piece that is made here in Morocco in the region of Casablanca and Tangier in the north of Morocco. We are the first producers in Africa for citrus and capers. We are, in fact, the first worldwide exporter of capers. We are also the first producer and exporter of fisheries in Africa, and 1/2 of sardine cans, you know, these sardine cans that you buy in Zagreb, or in Piran, or in New York, or in Sydney, or in Dakar, 1/2 worldwide is made here in Morocco. 1/2. is made in this country. We are first producer of fertilizers, phosphoric acid, and exporter of phosphate worldwide. We are the first touristic destination. Last year, we were the first touristic destination in Africa. 17.4 million of tourists came in Morocco. The target by 2030 is to exceed 25, and by 2050 is to exceed 65 million of tourists. Then we have the first high-speed train in Africa, the first digital payment company on the continent, and second worldwide. You know, when you use your credit card to withdraw money from the cash machine, the software that handles this operation that takes 10 seconds to 15 seconds, 1/2 worldwide, when you use your credit card, this software is made here in Casablanca. And the company is ranked second worldwide. We are the first investor in Africa, in Western Africa. We have the first or second financial market in Africa, and so on. This is not really an auto celebration. That's not the aim. We do have many problems also. We still have to reduce the poverty. We have big, huge discrepancies in terms of different regions. We have rich people and poor people. So we still have many problems. But what is written in red need a lot of energy, a lot of water, and this is why I felt that it was relevant to present this. So the challenges we are facing in Morocco, we have a growing energy demand and water demand for residential, industry, agriculture, transportation, and tourism. We are in a region where we have dramatic water scarcity with volatility of rainfalls, and our GDP depends on the sky. When it rains, it's a good year. When it doesn't rain, we are facing severe problems of development. We are importing currently 88% of our energy needs with a cost of $15 to $20 billion, which accounts for 1/3 of our national deficit. We have to decarbonize our industry to comply with EU standards and requirements if we want to export. EU is our first partner, and we export a lot to European Union, but we have to decarbonize our industry. And since we are the first worldwide producer of fertilizers, we are importing ammonia to make good fertilizer. If you ask me why ammonia, we can have this exchange during the question period. And we are the first. Last year, we were the first importer worldwide of ammonia. So we have to produce that ammonia. So Morocco has developed some strategies to face these challenges and threats. The first strategy is a renewable energy strategy with an investment of more than $30 billion by generating 52% by 2030 of the electric mix should be from renewable energies, and 96% by 2050. And we launched a huge program on green hydrogen with an investment of $32 billion. Since Morocco is the first producer in the continent of cars, we have a big partner partners with China and with other countries for producing batteries, electric batteries for electric cars. We are targeting water desalination because we don't have water. We don't have water in this country. It's a big threat for us. So but we have 3,500 of coastlines. So it's worth to make water desalination with a target of desalinating 1.7 billion meter cubic by 2030. And then there are some other strategies, 5, 6, and 7, and you have there the figures. So I will focus mainly on this part of electric cars, water desalination, and production of green hydrogen. So these are the projects that were implemented in Morocco. In the right side, you have all the projects that were implemented in Morocco for water desalination. In this region where we are, there is a project of desalinating 300 million cubic by year. By year, not by day. Not by day, by year. And the one in south of Morocco, in Agadir, 350 million meter cubic per year, and it is the largest in Africa. In the left-hand side, you have all the projects that were implemented for electricity, renewable energies. So the water that we are targeting, the objective that we are targeting by desalinating 1.7 billion meter cubic per year by 2030, and 2.4 billion meter cubic by year by 2050. This water, 50% of this desalinated water will be drinkable water. 30% is for agriculture, for irrigation, and 20% for industry. So let's start with green hydrogen. If you want to have green hydrogen, you need to have it from different sources. So classical sources, you have gasification of biomass, that is energy consuming kind of technology. You can use the steam reforming of hydrocarbons, but this generates carbon monoxide that will be most likely generate carbon dioxide, and it's energy consuming. Or you go with electrolysis. But if you want to make electrolysis of seawater, you cannot do it because you have different problems. I will explain the problems that makes not possible to make electrolysis directly from seawater. You need pure water. So if you need pure water, you have to go to desalination. You can make desalination by using distillation. This is, again, it needs a lot of energy because you have to heat water and to evaporate water, and then to make condensation of water, it needs a lot of energy. Or you make reverse osmosis that I will explain later on. But before making reverse osmosis, you have a multi-step treatment. You have to make some filtration, microfiltration, ultrafiltration to remove the organics and to remove the pathogenic agents like viruses, bacteria, microbes, and parasites. And if you want to use this water to drink, then you have to mineralize again this water, and to adjust the pH. It's an additional step in the process. So to do this operation, you need energy. We don't have energy in Morocco, so we use renewable energy from different kinds of renewable energies. Once you have this renewable energy, which comes from intermittent sources, you have to store it, so you need batteries. And I will explain all the technologies behind each block of this. And then, once you produce hydrogen, hydrogen is very volatile, it's very flammable, so you can store it. But how to store hydrogen? You can store it underground in salted environment, very complex technology. Or you can transport hydrogen, but hydrogen is very volatile. You need, whether you need to cool it down at low temperature, below 250 degrees Celsius, or you have to use high pressure. High pressure, when you say high pressure, is more than 300 to 700 bars, which is huge. Or you can transport hydrogen through chemical reaction. Because if you use hydrogen plus nitrogen that you can capture from the air, then you can obtain ammonia. Yet you need some catalyst, but this reaction is an equilibrium chemical reaction. So you can go from hydrogen, you generate ammonia, and once you have ammonia, which is liquid, then you can reverse the chemical reaction to obtain hydrogen. So this is what Morocco is doing. So, and let's see the applications we target from the production of green hydrogen. The first target is to produce ammonia, because we need ammonia for producing fertilizers. Our target is to produce 1 million tons by 2027 and 3 million by 2032 by the big Moroccan company with the name of OCP. Second target is to decarbonize the cement industry. Cement industry is using clay, is using concrete, but it generates a lot of carbon dioxide, and we should decarbonize using hydrogen. The third target is to reduce steel, and we produce steel in this country. Steel is iron. It has whether 2 degrees of oxidation, it's FeO2, or 3 degrees of oxidation, FeO3. When you have oxygen with iron, the mechanical properties and surface properties are reduced. So you have to remove oxygen. How to remove oxygen? You use hydrogen. Hydrogen plus oxygen, you get water. So to reduce the steel and aluminum industry. The fourth application we are targeting is to generate fuels like methanol and ethanol and other products like olefins. And if you have olefins, you can make a polymerization to obtain polyolefins like polyethylene or polypropylene, and that we don't have. The fifth application is to use green hydrogen to generate electricity, but for that you need fuel cells. And sixth application we are targeting, since Morocco has the largest port in Africa and in the Mediterranean, which is in Tangier. It's larger than the ports in France, or ports in Spain, or ports in Portugal, or ports in Croatia. Sorry to say, you beat us in football, but we are beating you in the port. This is the largest port in Africa, and the target is to use it as a green hydrogen station to fuel in the boats and the ships. So these are 6 applications for Morocco. So let me focus on these 4 blocks: fuel cells, electrolysis, batteries, and reverse osmosis. So, but before that, let me explain the problems and technological bottlenecks that we are facing using these technologies. First, when we pump water from the sea, we impact and we harm the ecosystems and the biodiversity. Mainly, we are pumping at the same time all the organics, and we are pumping also fish. So it's a big problem. There are presently some technologies like using ultrasound, but it's not yet mature technology. The big problem is once you have made desalination, what to do with salt? It's a big problem. Third, hydrogen is extremely flammable, and it poses the problem of storage and transportation, as I explained before. The fuel cells, I will explain, and the electrolyzers are very expensive. They suffer from problems of durability and reliability. I will explain this. And reverse osmosis, that I will explain also. It needs high energy, and you need to change all the time the filters because you have some glocking due to the different compounds that are in water. And to produce green hydrogen, even if you produce, you need between 8 to 11 of pure water. So people, they are talking about producing green hydrogen, but you need a lot of water. And we have a problem of batteries and so on. So let me start by fuel cells. You have different kinds of fuel cells. Depending on the temperature, if you use liquid water, you have different fuel cells that operate at different temperatures. You have anion exchange membranes, proton exchange membranes, and alkaline electrolysis, which is a very mature kind of technology. But it's very expensive, and it's not the most efficient one, but it's mature. The other ones need more development. And then, or you can work with vapor, and then vapor water, and then you have solid oxides kind of membranes that operate at very high temperature. And you have also differences in the second line. You have differences in terms of the operating pressure. So let me just take this one, a polymer or proton exchange membranes, explain it, and explain also what are the scientific and technological challenges. So a battery is, a fuel cell is composed of 3 components. You have anode and cathode. In between, you have a membrane. In this case, it's a polymer membrane. And then you come up, and then you have also 2 other components. You have a diffusion layer that brings the gases, and you have a bipolar plate that conveys the electricity. How it works? So look at the left-hand side. You have hydrogen that is coming. Once you have you made hydrogen from seawater desalination, you bring hydrogen. Hydrogens go through the anode. It meets a very thin layer of a catalyst that is platinum. And once it meets platinum, then hydrogen is decomposed into 2 protons, 2 H+, and 2 electrons. The electrons cannot pass through the membrane, cannot. So they have to go through external circuit generating electricity. And the protons, they diffuse inside the membrane. They come and they reach the cathode, and in the cathode you bring oxygen from the air, and then you have chemical reaction, hydrogen plus oxygen, it gives to you water and heat. So you have to remove heat, and you have to cool the heat. You need, again, water. 50% of the pure water we are using is for cooling. Only 44% is used to generate electricity. Which membrane is currently used? The most known membrane is Nafion. It's produced by DuPont company. It has some sulfonic acid groups. Sulfonic acid groups, you have oxygen, and oxygen, it has a lot of electrons, and these electrons attract the protons. There is no covalent bond between the hydrogen and the oxygen, because all these oxygens are involved in a double bond. So they attract the protons, and this is why there is this sulfonic acid group. The problems we have before that, so the fuel cell, in fuel cell, you start with hydrogen and oxygen, you use a catalyst, and then you produce water and heat. In electrolyzer, it's exactly the inverse. You use electricity to decompose water into hydrogen and oxygen. It's similar technologies. Electrolyzer is the inverse of fuel cells, with a little bit of some differences, but they are not major. The challenges is the cost of these fuel cells. They are very expensive. They have problems of durability, of reliability, and of performance. They undergo some problems of glocking, because you have many products that they glock the membranes, and you have problem of aging, corrosion of bipolar plates, and the stacking. What they have shown here is just one module. If you want to make a fuel cell, you have to bring different modules and you stack them. You stack them. And when you stack, you have problems, mechanical problems and electrical problems at the interfaces. And this is a huge problem. So we have to look for alternatives. So let me explain to you again how it is composed. These fuel cells, you have in between the polymer membrane, you have diffusion, gas diffusion layer, you have bipolar plates, and these are the problems of this Nafion. So what we proposed in the past, as I told you when I was young, strong, and handsome, we did some research, and now we have licensed this to a company with the name of Balar. It's one of the largest company in the world for fuel cells. It is a Canadian company, and we proposed PEEK, polar ether ketone, with some sulfonated acid groups, and it works a little bit, yet it has problems of aging, it has some problems of working at very, very high temperature, but it's much better than Nafion. And there are other potential electrolytes using some cyclic polymers, some nanocomposites, or some ceramics. And the bipolar plate, we are using presently some very expensive kind of materials. There is a possibility of using graphene-based kind of compounds, like graphene-based nanocomposites. So the potential alternatives, one of the big problems is platinum. Platinum is very expensive, very, very expensive. The advantages of platinum is excellent for any electrochemical reaction. It can be recycled, it can be reused. It's worth for different chemical reaction. It's an excellent catalyst, but it's very selective, but it's very expensive. It can generate nitrogen oxides, which are not good for the environment, and it can be poisoned with different cations and anions and carbon monoxide. Potential alternatives, potential research works that can be done in the field is to search for other catalysts using palladium, using silver, using even iron, or go for binary and ternary systems, methyl oxides, using zeolites. I will explain what does mean zeolites, and some metal nanocrystals. Let's go now to batteries. So I will focus on batteries. Batteries is exactly the same. You have the same components. You have anode and you have a cathode. But now, instead of having electrons or protons that are moving, you have ions. You have lithium, for instance, if it is lithium-based kind of battery. So the electrolyte inside is not anymore a polymer, is a liquid that really conducts the lithium ions. The problems is the problem of autonomy. So you cannot use this in a car. You know, the electrical cars presently, they suffer from the non-existence of good batteries with good autonomy. Personally, I cannot buy an electric car because when I travel, I am afraid that during my travel in the highway, the car will stop. So we need to increase the autonomy. The density of energy is small. The time of loading, to load and to charge a battery takes several hours. You have a problem of durability, problem of corrosion. If you see the batteries you have in your car, all the time you see some green liquid. This is the electrolyte that leaks, that goes from the battery and it diffuses outside. And this is a big problem. Recently, Tesla and Stellantis, they presented new kind of batteries based on lithium, nickel, manganese, and cobalt. And there is a recent publication by China, by a Chinese company, that claims that they can charge 60% of the battery within 10 minutes and with an autonomy of quite 1,000 kilometers, which is very interesting. Very, very interesting. And Morocco has partnered with this company to make a gigafactory in the region of Tangier. Other possibilities of R&D is to, instead of making liquid electrolyte, make a solid electrolyte. We are a country that produces phosphate. And you know, in between the anode and the cathode, what we are using presently is hexafluorophosphate, which is liquid, but we can make an electrolyte solid. So we can make an anode, a cathode, and the electrolyte, all this from phosphate. For the researchers, Moroccan researchers, this is a good area to work on. Very strategic for Morocco. We can use some other structures like carbon nanotubes, graphene, 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 and other components. Big field of research, open. Reverse osmosis. In osmosis, classical osmosis, on the left-hand side, you have water with salt. On the right-hand side, you have water, pure water. Classical osmosis is, since you have a different concentrations, or if you are a physicist, you will say different chemical potential of the two compartments of this reservoir, you will have diffusion of the salt from the left-hand side to the right-hand side. But this is not good. We have a semi-permeable layer that allows only water to pass through. So classical osmosis, water will pass from the right-hand side to the left-hand side. This is not good because this is, if we let just the osmotic pressure to play its role, you will have the diffusion from the right-hand side to left-hand side. So what we do, we will make a pressure such that we will force the water to go from the salted water to the pure water. And this consumes a lot of energy. You need a high pressure. High pressure, you have some glocking of the membrane because the chlorine will really stuck on the surface of the membrane. You need also to filter not only water, but the pathogenic agents like viruses. A virus, it has a size of between 10 to 400 nanometer. You need to stop the bacteria. Bacteria, they have a size between 0.5 to 50 microns. Whereas water, it has a size which is approximately 3 angstroms. So what you need some membranes with some porosity that you can adjust to let the water pass through, but not the bacteria, not the viruses, and not the salt. How we can do this? I will show you how I can generate some nanoporous kind of materials with well-calibrated pore size. I will show you how to make some pores of 5 angstroms. 5, 6. If you ask me to make a pore size of 7, I will make it for you 7, not 5, not 6, not 8, 7 angstroms. And we control the pore size, and the technology is really worth now to be used in this field. It was not used in this field. I will show you how to use this technology. Now, what to do with salt? Salt, you can store it underground to capture the hydrogen, to store the hydrogen. But salt should be valorized, and we need for some chemical reactions to convert salt into added value products. For instance, if you use nitrates, if you use salt plus nitrates, you obtain 2 products. One, it's chlorine of silver, which is antimicrobial, which can be used as disinfectant and antiseptics. And you have the last product, which can be used as a fertilizer. And if you heat it at high temperature, above like 500 degrees, you can obtain some pyrotechnic kind of products. So this is just one of potential chemical reactions. But we need research in this field, how to convert salt, because it's a big problem. Presently, what we do, we throw it again into the ocean. And this harms the biodiversity and harms the ecosystems. In our university, we are using also some direct osmosis. Instead of making inverse osmosis, there is a big team that is working on direct osmosis. We are developing some new electrolyzers. We have an ongoing patent, international patent, new technology. So now in this osmosis, as I told you, we need pressure. A pressure is a force by a surface unit. So if I want to maintain the same pressure, I can really decrease the load, the force, decrease the load by decreasing the surface. So basically, what we can do is to take a reservoir like the wires, you know, the electrical wires, the big electrical wires, where you have small wires inside with small diameter. So you reduce the size of these reservoirs by making small reservoirs inside the big reservoir, and you use the same, you have the same pressure, but you decrease the load, so you decrease the energy. Now, the challenge is how to make these new tubes. I will show to you how to use it. So there are different technologies how to use these very thin fibers and thin, you have electrospinning, but I will go and show you the nano design. How can I design this mesoporous kind of, this porous material to make it for filtration and also to make it for osmosis. The same strategy, and you generate three kind of products. One is for filtration and one is for osmosis. So I will start with this general phase diagram that reports temperature as a function of the concentration of surfactant. Here in the left-hand side, you have what we call a surfactant. It has a red head, which is made by an alcohol, acid, or amine groups that are hydrophilic. Hydrophilic, they need water. They are, if you put them in water, they like water, hydrophilic. But the tail is made of CH2, which is hydrophobic. It doesn't like water. So if you take this kind of molecule, we call it amphiphilic molecules, if you disperse this in water, and you have the phase diagram there, temperature as a function of the concentration of these amphiphilic molecules inside the water at constant pH. The true phase diagram is three-dimensional, but here it's constant pH. So at low concentration, you have individual molecules. This kind of spermatozoid kind of molecules, they are individually dispersed inside water. If you exceed a certain critical concentration, then the different individual molecules, they will come in close vicinity and they will form a spherical shape. Then if you increase the concentration, all these spheres, they will line up like in a string to make cylindrical kind of shape. If you increase further the concentration, all the cylinders, they will come in close vicinity and you generate hexagonal kind of configuration. If you go to high concentration, you generate a lamellar kind of structure. This is thermodynamics. So this phase diagram, the first person who did this phase diagram was a woman. A woman. Her name is Miss Pockels. She was German. And she was not allowed to go to the university because the society was misogynic and women couldn't go to the university. It was in 19th century. Miss Pockels. So she started to make experiments in her cuisine, in her kitchen. And she did a whole work, scientific work, very nice work, in her kitchen. And then there is a guy with the name of Langmuir. He took all his work, all her work, and he got Nobel Prize. But the work was done by Miss Pockels. And this kind of molecules, this is what you use in detergent to remove oil from water, to wash your dishes, is this kind of molecules. Now, I will take so I put these molecules inside water, I increase the concentration till I reach the micellar phase where you have these cylinders. Then I will bring a source of silicate. Silicate will condensate on the surface of the cylinders. And then if you increase the concentration, then you will have different cylinders that will come in close vicinity. And then, but if you are at high concentration, in this, when you have lamellar structure, you will obtain this lamellar structure. And then you can obtain different kind of structures. One of the structure is like clay nanocomposites. But if you are in the other side, when you have cylinders, now you have cylinders with the walls that are solid and the inner part is organic. What you do, you heat at high temperature, you degrade the organic part, and you generate this. So if you want, it's 5 angstroms. 5 angstroms, 5. Remember that the carbon-carbon bond is 2.54 angstroms. The bond between 2 carbons, it's 2.54 angstroms. Here it's like if you have just 2 carbon-carbon bonds. If you want to have 6 angstroms, how to do it? Very easy. I have to change the tail, this CH2, I have just to change the length. Yet there is a maximum of the length you can reach, because if you increase highly the length, then you will have what we call the folding. But within a reasonable range of length, you can really calibrate exactly the size of this kind of structures. You can obtain 5 angstroms. If you tell me 7, I will make for you 7. So this is, it's worth for catalysis, for making lasers, because I can filtrate the wavelength of the light. I can make water desalination, water filtration, and so on. How to obtain now the tubes? I will incorporate inside these porous materials some catalysts. It might be a nickel or cobalt. I will put it inside. And then I will bring a source of hydrogen. The hydrogen will diffuse in the channels, into these pores, and once they come in close vicinity of the cobalt, so I will bring, for instance, acetylene. Acetylene will diffuse in the pores. Once it comes in contact with catalyst, it will decompose into hydrogen and carbon. Hydrogen is very volatile and it will be removed in the process, and you have carbon. But carbon is tetravalent. It needs some neighbors to be happy. But here you have some channels, cylindrical channels. So it will not have 4 neighbors, it will have just 3 neighbors. And it will take the shape of these holes, and you generate carbon nanotubes with well-calibrated diameter. You can obtain also graphene, and here you have pictures. You can obtain a whole bunch of structure. Graphene is very important. How much time, Mr. Speaker, do we have? I still have some time? Yes. Okay, very good. So this is graphene. Graphene, it's very nice material. It has the highest electrical conductivity known today. So it can be used in electrical devices. It can be used in fuel cells, because in fuel cell part we have bipolar plates, and they can use this bipolar plate from this graphene. It has a high thermal conductivity and low gas permeability, which is nice. So I will show you some of the applications of this graphene in the topic I am discussing today. So I will go to using this graphene, how to extract energy from sea waves. This is new. There are different technologies. One of the technology, you have sea waves. You can use some devices that follow the direction of the wave. So from the waves, you generate a movement. This is known. You have other technologies that you use this waves to generate some pistons. But I will show you some new technology. I will use piezoelectric kind of materials. So we have developed this many years ago. The objective was not to convert the sea waves to energy, but at that time, we had a big project with a big Canadian company to make some patches, you know, for the people who want to stop smoking. You have these patches here. And the company asked us how to make very thin films to record heartbeats for the big sports. And combining with some Bluetooth kind of devices, and then there is a direct transmission of the beat heart to the doctor, and to follow exactly the beat hearts and the blood circulation using these very thin films like these patches for stopping smoking. So let me explain what is a piezoelectric material. A piezoelectric material is a material when it is submitted to an external stress, external compression. If you compress this material, then the material converts the mechanical load to an electrical output. Conversely, if you bring an electrical output, the material will expand or it will be compressed. We call this piezoelectric kind of materials. You have a density of charge. It is related to the applied stress. And the coefficient that relates the stress to the density of charge, what I call density of charge, when you combine, when you compress this material, there is circulation of charges. If you have circulation of charges, you have electricity. And the coefficient between the two, we call it the piezoelectric coefficient. So at that time, we had the following requests from the Canadian company. They asked us to produce a film which is very thin with a thickness which is between 60 to 100 microns. And a piezoelectric coefficient which is very high because the heartbeats do not generate very high stress, just small stress or small deformation. So you can really, you have to capture, you have to be able to transform this small deformation into a signal. So we need high piezoelectric material. We need a very low density, lower than 0.9, and we need a material that is very deformable. Because if the material doesn't deform, then you cannot measure the heartbeats. So a material that is very sensitive to small deformation and low cost. So if you go and you see what are the materials, existing materials that have at least very low modulus. Modulus, what I call modulus, is resistant to deformation. A material that has a very low modulus is very deformable. A material that has high modulus, you cannot deform it. So if you look at all the materials, in the y-axis you have what we call the Young modulus that measures the toughness and the stiffness of the material, and on the x-axis you have the density. So the majority of piezoelectric materials are ceramics, made of ceramics. See there is a circle of ceramics. They have a high modulus, very high modulus of few hundreds of gigapascal. This is not what we want. We want something it's in megapascal, not in gigapascal. The density is very high. We are targeting a density which is below 0.9. So if you look at in all known materials, you have polymers. You have like polyethylene and polypropylene. They have a density which is around 1, which is still good, but it's not what we are looking for. They have a low modulus, few gigapascals, but we are looking for megapascals, not gigapascals. So we have to reduce the modulus and we have to reduce the density. How to do that? We took, for instance, polypropylene. We generate some cellular structure inside this polymer. If you generate some voids inside the material, then you will decrease the density. And at the same time, you increase the deformability, you decrease the modulus. And if you use graphene, then the graphene will help you to convey the charges if you have some charges inside the holes. And if you compress this material, then you will have circulation of charges through graphene and you generate a piezoelectric material. So this is what we did. We took polypropylene, we put inside some charges inside the holes. How to do that? We bring a gas like nitrogen, we diffuse the nitrogen inside the voids, inside the cellular structure, and then we submit this to very high voltage. Then the nitrogen will give some charges. And if you apply on this material, if you apply, then the charges, let me show it again. If you apply a load, then the charges will circulate, and then you have electrical signal. So you convert a mechanical stress into an electrical output, in an electrical response. You will have a polarization. So, and this is what we call piezoelectric material. So this is what we did. How to do that? How much time I have?
You used your time, now it's your own mind.
Okay, so, okay. I am very good student, so I will stop with, so this is the material that we filled with some materials. We stretch, we have the voids, and then we have metallization. We use corona discharge, which is high voltage kind of voltage, and then we have this electrical material. So let me just show you, and I will finish. And this is the piezoelectric material we have manufactured and currently is used by Fizo Technologies. It's a big Canadian company. So I will finish here. I will not show the rest. So I will, okay? So I will finish with this. There is a very nice project which is we are implementing in our university. We call it Agritech. We got some financing from some agencies. We got more than 2 million euros to implement this on our university. The aim is to combine artificial intelligence with agriculture, to make smart agriculture. What I call smart agriculture is an agriculture that uses less water, that uses drop by drop, but not only drop by drop in the time needed, when it is needed, with exactly the same quantity needed. I was mistaken myself. I was thinking that if I have to bring water to the trees, it's better to bring it during the night because there is no much sun and there is no evaporation. Now, it depends on the tree, it depends on the fruits or what is this tree is for. And our researchers have shown there is a period of time, depending on the tree, where the water needed has to be given in that period of the day. Sometimes it's at midday, it's much better, but it depends on the tree. So what we are doing, we are trying to combine artificial intelligence with this kind of smart agriculture. We have some sensors. First, we sense the biotic of the soil to see what are the organics that are in the soil, what is the pH of the soil, what are the minerals in the soil, what is the humidity in the soil, and so on. You gather all the data about the soil. Then we sense the tree in terms of topological information, the size, the circumference, the height, and so on. And you have some DNA kind of analysis. You get everything that is connected to the tree. And then we sense the environment in terms of pressure, temperature, the direction of the wind, and so on. And once you have all this information, then you get some really, you can manage the quantity of water you give to the tree and the quantity of fertilizer and which kind of fertilizer. So we are in a country where we don't have water. It's a big problem for us. So this is good, and we are doing presently some hydroponic kind of agriculture, which is agriculture which is in vertically, not horizontally. And this kind of small devices were made in our laboratory by 3D printing machine. If you come to my university, which is Euromed University, we have the largest 3D printing machines in Africa. More than 100 kind of machines, and we are producing our own machines. We have implemented some of these machines in several countries, in Ivory Coast, recently in where? In Madagascar, in Democratic Republic, in Congo, in different countries, and even we will implement some of them in Portugal, and we are selling these machines. They were homemade by our own technologies, and so it will serve hopefully to agriculture. So I will finish my presentation by saying that in the field of energy, we are using renewable energies. Renewable energies technologies are quite mature. Yet we still need some development, but it's already implemented in different countries. And if you go in the south of Morocco, in Ouarzazate, we have one of the largest solar power plant in the world. And it's really in the south of Morocco. It's, I don't know how many kilometers of solar cells. So the technology is mature. In terms of water desalination, we still have to make a lot of research to enhance the electrolyzers, to enhance the osmosis, whether it's forward osmosis or reverse osmosis, and what to do with salt. Salt is a big problem, and we need some valorization of the outputs that comes from the desalination process. In terms of green hydrogen, we need substantial research and development. There is a room for plenty of research projects to do. Nothing is mature yet. So we need the reduction of water use. When you produce green hydrogen, you use between 8 to 11 liter of pure water to produce 1 kilogram of pure hydrogen. So we need to find ways in the process to reduce the consumption of water. The storage of hydrogen is a big problem, because whether you need to cool it at very low temperature or to make high pressure in tanks. So I heard, in Morocco at least, that people, they are working for hydrogen for mobility. Forget it. To be honest with you, forget it. Hydrogen is not ready for mobility. It's ready for mobility for big engines, for trains, for ships, for big trucks, but not for automotive, not for your car, for different reasons. We don't have any stations for hydrogen. We need to change everything. And we need to have hydrogen, and hydrogen, if you need to have it in the station, like petroleum station, you need high pressure. We don't know how to store it. So big opportunities for research, and we need to find applications for this green hydrogen. And I will stop here. And thank you very much for your presentation.
Thank you, Professor Bosumina, on this very nice lecture. Before the lecture, you said that energy scientists are the most important, so I will not disagree with you, but today you prove my hypothesis that the best energy scientists are chemists, because we know what forests do, but only you understand what is in roots and in roots. So I will now go to the public because we used all of your time and my time, so maybe just the audience gives some possibility to ask the questions. Okay, Professor Dujic, and then...
Thank you for excellent lecture. But I'm not sharing your pessimism about electric cars, batteries. I came from Zagreb with Tesla. It's 3,000 kilometers, and my plan is to continue all the way to Agadir to show that one can drive electric car in Morocco. And I'm doing it for maybe 10 years and never stayed without electricity. Let's see what Morocco brings. Because you can charge anywhere. You just knock on the door of a neighbor and say, can I get a little bit of electricity? And it works. But my question or my comment is more related to your excellent introduction, where one part is missing. What about carbon? If you want to become a big producer of fuels, carbon-based fuels, methanol, feedstocks, etc., you need renewable carbon. And there is an interesting paper by Christian Breyer about Egyptian case, where they propose using desalinated water to reforest parts of desert and use this carbon for production of fuels. What do you think? Does it fit Morocco?
Yes. First answer to your first comment, thank you very much. If you come from Zagreb, I visited Zagreb several times, very nice. Croatia is very nice. Was in Croatia when I was 16, when it was Yugoslavia. And now we have 7 countries, but it's wonderful, really wonderful. I got wonderful memories from Zagreb, from the neighborhood. So you are working with Tesla?
No, I'm just driving Tesla.
Driver of Tesla. So, yeah, perhaps for me, perhaps it's particular to me. I want to be sure that if I bring my family with my kids, I will not be stopped on the highway because my car doesn't have the required autonomy. But I do agree with you. We can stop anywhere and ask people to help you, but when you are on the highway, it's a little bit difficult. But I do agree with you. So Morocco is really engaged in that. We have a big project with the investment of $8 billion in the north of Morocco, in Tangier, to make a gigafactory for producing batteries. And that give more autonomy for the cars. As I told you before, it's approximately 1,000 kilometers, which is still very nice, and 10 minutes for charging 60% of the battery in 10 minutes. So it's very nice. Now, carbon, you are right. We have to use this carbon to use the fuels and what it is proposed in Egypt. Perhaps it's very nice. I am not aware about this. Another interest is that we capture CO2, the carbon dioxide, and to convert the carbon dioxide into methanol and or ethanol and any other alcohol or any paraffins or any olefins. So this is the way to go. But in Morocco, we have a problem. We are a partner of the European Union. And we do a lot of business with the European Union. But the European policy is not gentle with us. If you take carbon dioxide and you decarbonize your industry, all the products you generate with this European Union, they told you, no. This is not the true decarbonation. We tell them, yet we are capturing the carbon dioxide. No, you have to bring it from the biomass. So in Europe, between European countries, is accepted, but not for Morocco. So what is permitted, what is allowed between European countries, it's not allowed for us. So we are in negotiation with them because we are partners, big partners. We are at 14 kilometers. Morocco plays a crucial role for Europe to stop the immigration, to stop the terrorism, and also to open Africa. It's the first gate to Africa is Morocco. It's 14 kilometers. So it's best to be good neighbors. We are good neighbors for many, many centuries. And even in our constitution, and they will finish, in our constitution, the first article of our constitution that defines who are the Moroccans. First article of our constitution says that Moroccans are blah, 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 and Mediterranean, Euro-Mediterranean. We have the roots, we have African roots, but we have a European roots also. We are just in between. We are a convergence of different cultures, of different faiths, of different civilizations. Yes.
Okay. Thank you. There was another question.
Thank you so much, Prof. Mustafa. Thank you so much for your excellent presentation. Each part touched my heart because I am material science. I'm working with the nanotechnology, graphene, blah, 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 extra. Now, my question about RO. You mentioned about controlling about the porosity of RO. Any size, for example, 7, 6, 7. You have this scale up because we start a project to develop RO with shark skin sheep to reduce biofouling, to make it very strong in harsh climate like in Qatar. I'm a scientist at Hamad bin Khalifa University in Qatar. We work on this project. If we have collaboration to scale up this project, will be excellent project.
I will be more than delighted after the conference to discuss together.
Thank you so much.
Yes,
thank you so much for your presentation.
Thank you very much.
Okay, I can allow the last question if there is any. Okay, once again, thank you for this excellent lecture, and we hope that many of your proposals will again come into the practice and that new patents will come. And for Morocco, I can only say that you started to play good football, and in 2030 we know who will play in finals and we know who will win it. So thank you.
We will beat you in 2030.
Yes, okay. Thank you.
I'm joking. I'm joking.
I agree with that.
But you have good players. Modric is just amazing, but he will.
But
not
we are used for the second place, so we can take it. Okay.
Very good.
Thank you. And, now for the participants that are interested in today's tour and visit, we will have just a small announcement for this. Professor.
So good day, everyone. Thank you again for attending our first African conference, SDEWES. I would like to inform you shortly about our excursion today. Meeting point will be in front of hotel at 2:30. There will be 3 buses, and transfer to Ujda will be hour and a half. Please, for excursion, bring your sun protection hats, scarves, sunscreens, and of course water. And we'll come to Ujda, we will have a guided city tours. So please, it will be on foot and wear comfortable shoes. Office exchange and ATM will be on our way to local fair and La Souk. So after the fair, the dinner will be held at 8 o'clock in the evening at Riyad Dar Septi. This is a nice historical place, so please grab a spare shirt or anything that you would like to change. And the transfer back to Hotel Saidia will be organized at 10 o'clock with buses. For those who want to continue socializing when we come back to hotel, the bar on the right of reception will be open. And for all of you who still didn't gave us your passport ID and you want to go with us today to excursion, please sign up at our registration desk. For anything else, our last staff is here to help you, guide you all through the way and make you feel safe and welcome. And we have an extra information. We have a person who lost his phone. So if you know someone in hotel looking for it, please let them know it's at registration desk or to ask for Katarina. I will bring it with me to the trip. So for everything else, I hope you'll have a good day today and thank you for your time. See you. Go have a lunch. Enjoy.
Yeah, we do use it for furniture or unfortunately now also a lot for energy, which is not the best way. But we need to build forest economy because later carbon will be used for fuels.
This is something that specialists for Austria, they have a company that produce most of the paper. So they
now stopped or started to slow down the use for energy because they need more paper. European forests are heavily used.